In this video, we are going to look at the entropy change of pure substances that is discussed in section 7-3 of the book. Now we have seen that the liquid vapor phase diagram for water, which you have seen as the dome, and you have your compressed liquid, saturated liquid vapor mixture, saturated liquid, saturated vapor, and then superheated vapor region. And here is the critical point above which there is no distinction between liquid and vapor states. You can plot the same curve in temperature entropy diagrams. That is, you can think of the same TV diagram or T nu diagram in which we calculated or plotted the phase diagram, and here we are going to plot it in terms of TS diagram, temperature, entropy, wherein each curve a curve of constant specific volume is denoted and then curves of constant pressure are denoted similar to what they were previously, and so on. So just like we calculate other properties like internal energy or enthalpy or specific volume, we are going to calculate the entropy that is calculated for different temperatures and pressures. And for water, this is tabulated in tables A4 to A6, like we did before. So you can read up the entropy of a compressed liquid, which is approximately the entropy of the saturated liquid at the same temperature. You can look up the entropy of a saturated liquid vapor mixture as the entropy of a saturated vapor times X plus 1 minus X times the entropy of a saturated liquid. And then you can also look up the entropy of the superheated vapor. All these can be looked up, and if you have two states, you can look up delta S as S2 minus S1. S2 minus S1. As we draw TS diagrams, you can think of temperature and entropy, which is in joule per Kelvin. And a phase change process, like for example, if you have your dome, a phase change process during phase change is going to be taking place at a constant pressure and a temperature that is equal to the saturation temperature. This process involves an entropy change, specifically entropy increases during phase change. I'm going to put an arrow here, during phase change. Why does entropy increase during phase change? You are going from a liquid-like state. You're going from a liquid-like state to a vapor-like state where the molecules are even less bound, they are more chaotic, and there is even less cohesion between them. They occupy the entire volume and so on. So entropy increases during phase change. And this process is shown as moving from left to right in a TS diagram. You can also think of a process in which entropy remains constant. So if you have a TS diagram, let's say you have state 1 here, you can go up to state 2, and during this process the entropy remains constant, and such a process in which entropy is constant is called an isentropic process. This is a process in which entropy remains a constant. Entropy remains a constant. And when would that be true? So if you take delta S to be equal to 1 to 2 delta Q over T plus S gen, entropy would remain a constant if the left side is 0 and the amount of heat transfer exactly matches the entropy generation, or in other words, if the internally reversible heat transfer between the two states is exactly equal to minus S gen. We will see cases of internally reversible heat transfer in which entropy change is 0, which can be modeled as isentropic processes, or in reality processes in which frictional effects or other irreversibilities are negligible, and those that are reasonably adiabatic. That is, the heat transfer is approximately 0. That is, if you have a reversible adiabatic process, is an isentropic process. It has to be both reversible and adiabatic. If it is only reversible but not adiabatic, or it's only adiabatic but not reversible, then it is not an isentropic process. So you can say all isentropic processes are adiabatic, but all adiabatic processes are not isentropic necessarily. An isentropic process delta S equals 0 or S2 equals S1 is usually used as a model for frictionless adiabatic expansion or compression devices, those in which the work is non-zero but the heat is 0 and no friction or minimal friction. Okay, it's a model. Isentropic process is a model for work or input or output devices in which the heat transfer is minimal and frictional effects are also minimal. Entropy is used as a coordinate to mark different processes. In this course so far we have seen pressure, volume, we have seen temperature, volume. The other type of process diagram you also used is temperature, entropy. These are all state variables. They can be used to determine the position of a state. And then there is also a type of chart known as Mollier charts, which are enthalpy, entropy diagrams, temperature entropy diagrams, temperature specific volume diagrams, and then pressure specific volume diagrams. So the one more type that I left out here is internal energy and enthalpy diagrams. So in the beginning of the course, I told you the state variables are pressure, temperature, specific volume, internal energy, enthalpy, and entropy. And any two can be used, any two can fix a state. Any two can fix the state. So the same state can be determined by any two of these, and the remaining four can be determined through the state equations. And usually, which two to be used is selected based on the process. For some processes, it's natural to select PV or TV or T nu. For some processes, it's natural to select TS or HS. For some processes, it's natural to select U and H, or internal energy and enthalpy. Next, we are going to look at what is called as TDS relations, temperature entropy relations. So if we begin by writing the first law for a internally reversible process, think of the heat transfer that is internally reversible minus the work output that is also internally reversible. This should be equal to the internal energy change. But the definition of entropy is that delta Q internally reversible divided by T equals ds, or delta Q internally reversible equals T times ds. Okay, and the work can always be written as P dV or d nu. Okay, so I have TDS minus P dV equals du. Okay, so I can rewrite this as ds equals du plus P dV divided by temperature. Okay, this equation is general. It doesn't assume any material. It can be for solid, liquid, or gas, and it's called the Gibbs equation. Okay, I'll write it again. ds equals du over T plus P dV over T. Now in this relation, I can bring in enthalpy, which is again another constructed quantity, as H equals U plus PV. Okay, I can write dH equals du plus P dV plus V dP or mu dP, and I can write ds equals du plus P dV divided by T, which is dH minus nu dP divided by T. This is another relation. This is another version of the Gibbs relation in terms of enthalpy. Both this equation and this equation are both Gibbs equation in enthalpy in an internal energy form. Okay, so you can use it. You can use Gibbs relation. Gibbs relation can be used to calculate entropy changes through dH or du. That is, ds equals du plus p dv divided by t. Now, for simplicity, let's consider for liquids and solids. What is the relation between internal energy and change in internal energy is specific heat times the change in temperature. So I can write ds equals du plus p dv divided by t is c times dt divided by t plus p dv divided by t. Okay. And if you consider solids and liquids, they are also incompressible, which means their change in volume is 0. So ds is simply c dt divided by t, or delta s, which is s2 minus s1, is integral t1 to t2 c dt, or specific heat times change in temperature. This divided by t. This divided by t. So I can write this as, if I have constant specific heat, this is c naught times natural log of t2 by t1 if c naught is a constant. If it is not a constant, then I would need to go through the integration as per this equation. Not specific heat a function of temperature. Okay. For an isentropic process, if the process is isentropic, I have delta S equals 0, which implies T1 equals T2. That's the only possibility by which delta S can be 0. So in this case, isentropic also implies isothermal. Okay, this is only for liquids and solids. Liquids and solids. Now we can do the same analysis for an ideal gas. What is true for an ideal gas? P equals RT over nu. Okay, I'll start with ds equals du plus P dV divided by temperature, and du equals Cv as a function of temperature times dt. So ds equals Cv as a function of temperature times dt plus P, which is RT over nu times d nu divided by temperature. So I have ds equals Cv of t dt divided by t plus r d nu over nu. Delta S would be integral 1 to 2 of ds, which is t1 to t2 Cv of t dt over t plus nu 1 to nu 2 r d nu over nu. So this is equal to t1 to t2 Cv of t dt over t plus r natural log of nu 2 over nu 1. If Cv of t is a constant, we'll call it Cv naught, then the integration is simpler. Delta S is Cv naught times natural log of t2 over t1 plus r times natural log of nu2 over nu1. Otherwise, then we'll need to perform the integration as per the formula. The same result may be written in terms of the pressures. Delta S is 1 to 2 Cp of T dt minus R ln P2 over P1. The next relation we want to derive is that of what is the equation of what is the process equation for the isentropic process of an ideal gas. That is, ideal gas implies you can write P equals RT over nu. Isentropic implies delta S is 0 or S2 equals S1. Okay, so delta S you can write it as ds can be written as du plus P dV divided by temperature. We do know that ds is 0 because it's an isentropic process. So I have du over T equals minus P dV. So this is Cv over times T dt divided by T equals minus R dV over nu, d nu over nu. So if I assume Cv of T or specific heat at constant volume is a function of is a constant independent of temperature, I can write dt over T between 1 to 2 equals minus R over Cv naught from 1 to 2. Okay. So this is natural log of T2 over T1 equals minus R over Cv naught natural log of nu2 over nu1. This is log of nu1 over nu2 divided by Cv naught divided by R, or T2 over T1 is ln of nu1 over nu2. It is equal to nu1 over nu2 Cv naught divided by R. Now we do know something about Cv naught, which is Cp naught minus Cv naught equals R. Okay, so let's define Cp naught divided by Cv naught to be K, ratio of specific heats. Okay, so I have Cp naught minus Cv naught equals R, Cp naught divided by Cv naught minus 1 equals R divided by Cv naught, or R divided by Cv naught equals K minus 1. Okay, so I'm going to use this in this relation. T2 over T1 is nu2 over nu1 to the power R divided by Cv naught, which is nu2 over nu1. R divided by Cv naught is power K minus 1. Okay, power K minus 1. I'm sorry, it's not K minus 1, it's 1 minus K. So if you simplify this for an ideal gas, you can either write it as T2 over T1 is nu1 over nu2 power k minus 1. You can also write it as T2 over T1 is P2 over P1 power k minus 1 over k, or you can write it as P2 over P1 equals nu 1 over nu 2 power k. Most common form of this is P nu power k is a constant for an isentropic process of an ideal gas. So if it is said that the ideal gas, the moment you see the word ideal gas, you can assume that this is true. The moment you see the word that it's an isentropic process, it is true only for that process. Okay, so this is a process equation. This is a equation of state, equation of process, equation of state. Okay, so it's either written as PV power k is a constant. It is also written as T nu power k minus 1 is a constant, not the same constant, it's a constant, or Tp power k minus 1 over k is a constant. So all these three forms are isentropic equation of equation with the ideal gas being PV equals RT. This also comes with the assumption that the specific heats are constants and K is the ratio of the specific heats at constant pressure and at constant volume.